Hi there. This video is on section 11.5 and also the beginning of 11.6. I'm going to be helping you determine if an alternating series converges using the alternating series test. And a very related idea is to determine if a converging alternating series is conditionally convergent. So even though that's in 11.6, it's really closely related to 11.5. So I'm going to be doing them both in this video. Okay, so first of all, we need to define some terms I'm using: alternating series tests, conditionally convergent, etc. So I'll do that in the beginning so you get an idea of what we're talking about as we do some example problems. Okay, so I have a little note here. An alternating series is a series in which the signs, the terms alternate positive, negative, positive, negative. They go back and forth, right? So it just has to be some alternating version of positives and negatives. And then we have the alternating series test. The alternating series test has basically some conditions. It only applies to alternating series. So you have to assume that you're talking about an alternating series. Then, if you also have the fact that if you ignore all the negatives, just look at all the positives, like make everything positive, that's the absolute value. If those values on the series are decreasing, and the limit of all those terms of the series is equal to zero, then we immediately know that this series converges. So very actually easy to show that an alternating series converges using the alternating series test. If it's alternating, all you have to do is get rid of all the negatives, show that the values are getting smaller, and then show that the limit's equal to zero, and you know it's converging. Now, that is the answer. It converges. Now, there are some sort of subtleties that they want you to know, which is the difference between conditionally convergent and absolutely convergent. So we have conditionally convergent and absolutely convergent. And they all have to do with, okay, now that we know that an alternating series converges, right, let's look at the related series without all the negatives. So once we know that an alternating series converges, we get rid of all the negative signs. So just to look at all the positives. If it still converges, right? Oh no, excuse me. The first part here is if it now diverges, then we call this conditionally convergent. If it still converges, all right, then we call it absolutely convergent, right? So I'll just emphasize this, right? The non-alternating series diverges. So if you get rid of the alternating part, just have them all positive. So if you start with a converging alternating series and you get rid of the negatives and now it diverges, we call that conditionally convergent. However, if you get rid of all these negative numbers, make them all positive, and it still converges, we call that absolutely convergent. Perhaps some examples will clarify that some more. So let's start looking at some examples. Okay, so I'm going to be looking at maybe half a dozen problems here and determining if each is convergent, conditionally convergent, absolutely convergent, or perhaps just divergent and it doesn't converge at all. All right, so my first example here is this example A, little a right here, which says the series from 1 to infinity of -1 to the n over n. Now, I do recommend that students do this, although it's not required. I recommend you write out a few terms like n equals 1, n equals 2, n equals 3, just so you can start seeing what the pattern is. Sometimes it really helps to see what's going on to help guide you as to what direction you want to go in. So if n equals 1, I get -1 to the 1 over 1. -1 to the 1 over 1 is, well, -1 to the 1 is -1, -1 over 1 is -1. All right, so -1 to the 1, -1 divided by 1 is -1. N equals 2, we get -1 squared over 2. -1 squared is +1, so we get 1 over 2. And here we're getting -1 cubed over 3. -1 cubed is -1, so we get -1 over 3. And you might already see the pattern. -1 to the fourth is going to be a +1 and over 4. So the terms in this sequence that we're really adding up are -1, +1 half, -1 third, +1 fourth. This is an alternating series. And we know that's kind of come from like a -1 to the n, because when you have like an even number of negative ones you're multiplying, it'll be a positive one. When you have an odd number of negative ones being multiplied together, the result is a negative one. All right, so this is definitely an alternating series. So let's briefly look back up the alternating series test. There are three things. It applies if it's alternating, which we just did. It's alternating. The values have to be decreasing. And the values we mean when we get rid of all the negative signs. So just look at all the positives. Are they getting smaller? And then the last one is, so are they decreasing? Do they get smaller over time, over n, as n gets to infinity? And as we go to n equals infinity, do those decreasing values go to zero, right? Does the limit equal zero, which is our divergence test, right? That it has to pass the divergence test anyway. Otherwise, we know it automatically diverges. Okay. So we know it's alternating. We got that done. Let's look at the terms decrease. Do the terms decrease? And when we're talking about the terms, let me make this look a little more readable. When we're talking about the terms, again, we're talking about the absolute value of the terms, right? We're getting rid of all of the negative signs. So in this case, this becomes 1, 1/2, 1/3, 1/4. So are these numbers decreasing? And the answer is yes. The denominator is getting larger. Getting larger. And as we know, when you have a larger denominator, it makes a smaller fraction, smaller number. Denominator is getting larger, so the fraction gets smaller. All right, so then we know that the terms decrease. Yes, we do. So decreasing. If I could spell, it would be very helpful. Okay, so it's alternating, it's decreasing. The third thing we have to check is that the limit as n goes to infinity is equal to 0. So we'll try the limit. What about the limit? Goes to 0? Question mark. So what we'll do is take the limit as n goes to infinity of our series here, our sequence of numbers that we're adding up. It's a -1 to the n over n. That's our sequence of numbers that we're making into a series to add up. And all we have to do is show that the limit is equal to 0, and we're good to go. The negative signs almost never make a difference. And as you'll see in all the examples I'll be doing today, they don't really matter either. So what are we doing here? We're allowing n to go to infinity. So this is -1 to the infinity over infinity, right? So that's what our limit is going to. And we know that when the bottom goes to infinity, the number divided by infinity gets extremely small. So we're saying this most likely goes to 0. Technically, -1 to the infinity is an indeterminate form. So what you would do is you would just do a little like squeeze here, saying it's between -1 over n and +1 over n. We've done this before in a previous video. If you watch my previous videos, -1 to the n is between -1 over n and +1 over n, because -1 to the n just goes between positive and negative. When I take the limit as n goes to infinity of -1 over n, I get 0 because it's -1 over infinity, right? I'll just write that -1 over infinity thing. So we get 0. When I take the limit as n goes to infinity of 1 over n, I get 1 over infinity. And 1 over an infinitely large number is definitely 0. So we now know that whatever the limit of this thing we're looking for is, it is greater than or equal to 0, and it's less than or equal to 0. Well, the only way something can be greater than 0 and less than 0 is to actually equal to 0. So this is how we do the squeeze rule to show that officially. But like I said, honestly, we don't care much about the negative signs that really affect these kinds of limits. But really, mathematically, you should be doing the squeeze rule to show that definitively this is equal to 0. So we have satisfied all three conditions. Limit as n goes to infinity goes to 0. That's a check mark. So we've satisfied all three conditions. It alternates, the terms get smaller, and the limit as n goes to infinity of those terms go to 0. So those are the three conditions. So immediately we know that this, so therefore, thus, our original sequence, which was n equals 1 to infinity of -1 to the n over n, converges. And we'd like to have the reason why by the alternating series test. I'm just going to abbreviate AST because I know my handwriting is bad, and that avoids having to write out all those words. So that is a standard idea behind the alternating series test. It alternates, it gets smaller, the limit goes to 0, boom, we know it alternates. Okay, so now that we know that it alternates, we can now do the follow-up question is, does it, now that we know it converges, now we can do the follow-up question is, does it converge conditionally or does it converge absolutely? Right? So if it's converging, we can ask a follow-up question. Okay, good enough, it converges, but does it converge absolutely or conditionally? So what about, so is it, oops. All right. Oh, so I got to pause to fix my pen again. Sorry about that. Okay, back. Is it conditional or absolute? So these are the types of converging alternating series. An alternating series that converges can do so conditionally or absolutely. And all we have to do is just find the limit as n, we don't have to find the limit. We have to find the series of -1 to the n over n. Is this converging or diverging? Let me write them in opposite order. So is it diverging or converging? And please note that we're not just looking at the original series, we're looking at the original series with all the negatives thrown away. So we call it the absolute value of an. And diverging would be called conditional, and converging would be called absolute. So we have these, like, we have this follow-up question, like get rid of all the negatives, see if it's still converging or diverging. If it's diverging, we call it conditional convergence. And if it's still converging, we call it absolute convergence. All right, so if I get rid of all the negative signs came from the -1 at the end. Remember, when we did all the writing out of the terms, the bottom number was just n, didn't really have to do with the negative signs. The negative signs were all that part, that top part, the -1 to the n, which may make sense if you think about -1 to the n as n changes from even to odd. So we're trying to find this 1 over n. Get rid of the negative parts, right? 1 over n. And you can put the limits in here if you want. It doesn't really matter that much. So what do we know about the convergence or divergence of the series 1 over n? Well, if you remember this, if this looks familiar, this is called harmonic series. And it diverges, and you could just say because it's harmonic, but you can also say it diverges because of harmonic, or you could say by the p-test with p equal to 1. There's different ways of showing that it diverges. I'd recommend, if you recognize it harmonic, to say, hey, it's harmonic. We know harmonic diverges through lots of different tests. If you don't recognize it, then you can use the p-test. You can use an integral test. You can use different tests to show that it diverges as well. So we know that the original series, with the negatives in there converges. And we know that the series with no negatives in there diverges, right? So we know that the original series converges. And we also know that the series without the negatives diverges. So this is called, do you know what it's called? Conditional convergence. So that's the game we play. We try to evaluate this series, whether it converges or not. They're going to be alternating series for the most part, so we can use the alternating series test. If it diverges, we're done. If it converges, then we can do the additional question of us, what type of converging alternating series is it? Is it a conditional convergence like this one was, or is it absolutely convergent? And all has to do with whether you strip away the negative signs, and now the new thing diverges. It was called conditional, or it still converges. It's called absolute. Okay, hopefully that's not too much of a word salad. Let's do some more examples. So maybe it'll become a little bit more common in terms of how we think about these and what names we use for them. Okay. Example little b here. We have a series. You can see the -1 part. So we're saying, hey, that probably does some alternating thing. So again, may not be necessary. A lot of people say, hey, this is just a waste of time. I've been doing this stuff for a long time, and maybe I'm just old. But a lot of times just plugging some numbers really helps. So if you're getting stuck and you haven't plugged in numbers yet, yep, you might want to try it. -1 to the 0 plus 1 is -1 to the 1. Then we get 0 squared, and then we get 2 times 0 squared plus 1. Well, we have 0 on the top, the whole thing's 0. 0 is neither positive or negative, so n equals 0 doesn't do anything. So let's go to n equals 1. N equals 1, we have -1 to the 1 plus 1, which is -1 squared. Then we have 1 squared, and then put that in parentheses. We have 1 squared, and then on the bottom, we have 2 times 1 squared plus 1. -1 squared is +1 times +1. We have a 1 on top. 2 times 1 squared is 2 plus 1 is 3 on the bottom. So we have 1/3 is that n equals 1 term. N equals 2. I'll just do this real quickly. -1 cubed is negative. 2 times 2 is 4, so we get -4 on the top. On the bottom, we get 2 times 2 squared, which 8 plus 1 is 9. So -4/9 is the next term. And the last one, we're going to have, it's going to be -1 to the 4th, so it's going to be a positive number. We're going to have 2 to the 4th, so it's 16 is going to be on the top. And the bottom, we're going to have 2 times, whoops. Okay, I did that too fast. Pretend I didn't do any of that stuff. You're like, where did you get that 16 from? Okay, so I was going to do it fast, and then of course when I do things fast, I make mistakes. So the function on top is -1 to n plus 1 n squared. So when n is equal to 3, it's going to be 3 squared, which is in fact 9. So 9 on the top, and the bottom I get 2 times 3 squared plus 1, which is 2 times 9. 18 plus 1 is 19. Okay, there we go. And then, you can kind of see they're going positive, negative, positive, negative. Remember, 0 is neither positive or negative, so you can't include this. This is a positive number, negative number, positive number. You know it's going to be positive, negative because -1 to the n plus 1, again, is that traditional kind of thing. When you have a even number of negative ones, it comes out to be a positive. When it's an odd number of negative ones that being multiplied together, it comes out to be a negative. Okay, so alternates. Check. Do the terms get smaller? Do the terms get smaller? And do the terms go to 0? Well, for the terms getting smaller, again, we take the absolute value. And for the limit, we don't really care about the negatives too much, but we just take the limit of this thing. So how do we see if the terms get smaller? Now, the denominators are getting bigger. We know we have a larger denominator. It makes the fraction smaller. But the numerator is getting bigger, right? So the terms are 1/3, 4/9, 9/19, and we can try to see if they get smaller, but it's not obvious like the last one because both the bottom and the top are getting larger. So we don't know if the terms are getting smaller. So this should be, of course, terms getting smaller. Let me write a little smaller in there. Uh, so this one's not as clear that the terms get smaller. What about the limit going to 0? We need to find the limit as n goes to infinity. Again, we don't really care about the negative one part. I'm going to suggest you just ignore it because it really doesn't come into play with these limit problems. We just use a squeeze theorem anyway every single time, so it comes out the same way every single time. So let's look at this limit as n goes to infinity of n squared over 2n squared plus 1, and we want to see if that goes to 0. So, well, the top goes to infinity. Infinity squared is going to be infinity. And the bottom goes to infinity because 2 times infinity squared is infinity plus 1 is still infinity. If it's infinity over infinity, we can use what's called L'Hopital's rule. So we use L'Hopital's rule to simplify this, which means you can now find the derivative of the top function and the derivative of the bottom function separately, and the limit of those fractions will still be the same, equal to the original limit. So limit of the top, or the derivative of the top, is just 2n. The derivative of the bottom is 4n. Plus 1 goes to 0, right? So we have a limit as n goes to infinity of 2n over 4n. These n's, n divided by n, is equal to 1. So this is equal to the limit as n goes to infinity of 2 over 4, which is a half. So what is the limit as n goes to infinity of 1/2? Well, there's no n's in it anymore. All the n's divided out. So you just have a half. Half doesn't care what n is. If n is 1, it's a half. N is 2 is a half. And it's just a half. It's always a half. So this answer is a half. And I do have some news for you. A half is not equal to 0. And why is that important? Because we need the limit to go to 0 in order for this thing to converge. In fact, by the divergence test, we immediately know that no matter what this thing does, alternates, or whatever it wants to do, if the limit as n goes to infinity of those terms is not equal to 0, we immediately know it diverges. All right, so this original series, I'll just say original series, diverges. And we can say by divergence test if you want. I did want to show you this example because you don't have to do these in order, right? It's alternating, the terms get smaller, and the limit goes to 0. You can do it in any order you want. So if it's tough to do the terms getting smaller, I wanted to show an example where, why don't we just test the limit first of all? And if the limit's not equal to 0, we don't have to test the terms anymore because we already know it diverges. Also, because it diverges, we don't talk about conditionally convergent or absolutely convergent because it's not convergent, right? So there's no version of convergence. It is divergent no matter what. So we don't even answer the question of what happens. You get rid of the negative signs, it's going to diverge, it's going to diverge, we're done. Okay, so that was my second example. Let's do another one. Okay, oops, let me get rid of that smudgy thing and that circle. There we go. So for example C, let me zoom in a little bit here. We have 2 cosine pi n over n root n. We don't have a negative 1 to the n, so it's possible this does not alternate. We have to make sure that if we're using alternating series test, it does in fact alternate. And once again, I will demonstrate writing out some terms. All right, let me try to get to a proper pen. N equals 1, n equals 2, n equals 3, etc. Write out some terms, right? That's my suggestion. So for n equals 1, what do we have here? We have 2 cosine pi times 1 is pi, and n root n is 1 times root 1. So what is cosine pi? Well, it's good to have basic trig angles trig angles, trig ratios memorized. Cosine of pi, pi is 180 degrees or pi radians. So if you think of the unit circle, pi radians is halfway across. It's on the negative x-axis, basically. It's at -1. Cosine asks for the x value. The x value there is -1. So this is 2 times -1, which is -2 over 1 times √1, which is 1. If you want to grab your calculator and do cosine pi, that's fine too. You will get -1 as long as you're in radian mode, which calculus has to do with radian modes, radian angles. So that is -2/1. We got a negative number out of it, even though there was negative in the original formula. Let's see what happens for n equals 2. So we get 2 cosine of 2 pi over 2 √2. Cosine 2 pi ends up being +1. That's because you go full way around the circle. So you're back to the positive x-axis, where on the unit circle, the x value is 1. So we get a +2, and we get 2 √2 on the bottom. On the next one, we're going to have 2 cosine 3 pi, which is going to be 1 pi, 2 pi, 3 pi, back to -1 over 3 √3. And the next one's going to be positive, not -1, -2, because it's 2 times cosine 3 pi. So 2 times -1 is -2. And the last one is 2 times cosine 4 pi, which is +2 over 4 √4, which you could also write as 8, because √4 is 2. But it doesn't really matter. We just need to see what's going on here. So it is alternating. We have that down. Alternating. Okay, so we know that we're going to be looking at the alternating series test, and we have to find out, do the terms, the absolute value of the terms, do they decrease? And does the limit of this this crazy stuff, whoops, pi n over n√n, does this thing go to 0, right? Those are the two components we need to test for our alternating series test conclusion. All right, and it doesn't really matter the order. Let's look at the decreasing one. The decreasing one, remember, we only need to look at the absolute value of the terms. We can get rid of all the negatives. So I'm going to write out, let's get more space over here. I'm going to write out the terms, but without the negative signs, and then you'll, I think, quickly see what's going on. So we got 2 over 1, 2 over 2 √2. Remember, I'm not writing any of the negatives. I mean the absolute value of all these things. 3 √3, 2 over 4 √4. Do you see how the denominators are getting bigger each time, but the top numbers are staying the same? So we got 2, 2, 2, 2 on the top. The bottom is getting larger and larger and larger. So larger, larger, larger. So if the bottoms get larger, that means the fractions themselves are getting smaller, right? Anytime you have a larger denominator, 1/2 versus 1/5, all right, the larger denominator, 1/5, is going to have a smaller fraction. So terms decrease. And that's the second thing we needed to show. We need to show it alternates, which we did. We need to show the terms decrease. We did. We need to find the limit. Limit as n goes to infinity of 2 cosine pi n over n√n. We know this part is alternating between not positive and negative. So as I said, we can just ignore that because it just means you'd use the squeeze rule, and it's the same every time. So we'll do 2 over n√n as our limit that we're looking for. So what happens here? Well, we get 2 on the top, and on the bottom we have infinity times the square root of infinity, which is infinity. So this limit goes to 2 over infinity. 2 divided by something infinitely large goes to 0. Okay, so we know it alternates. We checked. We know it decreases. We argue that it decreases because the terms on the bottom get larger, so the fractions themselves get smaller. And we found the limit, and the limit goes to 0. So what does that mean? Well, if all those things are satisfied, we immediately know that this thing converges. So thus, the original series, so the original series converges by the alternating series test. Now, if it converges, right, this was our series right now that we're testing, right? So if the series converges by alternating series test, Then we can sort of do the follow-up question. So is it conditional or is it absolute? So if your alternating series converges, they will sometimes ask you on homework or a test or something, is that convergence conditional or is it absolute? And the way we do that is we do the series without the negative signs, right? We do the series of the absolute value of this original series. And as we saw by writing out some of the terms, the only thing that made the things negative or positive were this cosine part. So we're really looking at the series of 2 over n root n. Right? And again, you can write the numbers near if you want. You don't have to write. It doesn't really matter very much. So we're looking to see if that series converges or not. So now you have to kind of go back to the previous sections in chapter 11 when we talked about these different kind of tests, geometric series test, p-test, integral test, divergence test, all these different things to see if this thing converges or not. So this is a little bit, you have to kind of think a little bit about which test may apply. We can algebraically combine these things together because n times root n, these are both powers of n. So we get n to the 1 times n to the 1/2, which is n to the 3/2. Let me write that a little bit bigger so it's easier for folks to see. And that, if you simplify it algebraically, may ring some bells, may give you a hint that you can use the p-series test to see if this converges or diverges. With p equal to 3/2, with that number greater than 1, we know that the series converges. P is greater than 1, so this series here converges. And that's by the p-test, p-series test. So we have a series which, we have an alternating series which converges. Also, when we get rid of all the negative signs, we have a new series with only positive signs that also converges. So we have converging by the alternating series test. When we got rid of all the negative signs, it still converges. So if it converges by alternating series test and it still converges after you get rid of the negative signs, we now call this absolutely convergent. So the original series, maybe I should write it down, but I'm just too lazy right now, is called absolute convergence. All right, so this is an example of absolute convergence. We had an alternating series which converged, and with the negative signs, it still converged. And so this original series, if I can scoot over here a little bit, maybe zoom in a little bit. This was example little c. This 2 cosine pi n over n root n is an absolutely converging series. All right, so hopefully you get an idea of these things. I showed you a conditionally convergent alternating series. I showed you a diverging alternating series. I showed you a absolutely converging alternating series. So that's kind of the main idea. If you start feeling confident, of course, you're welcome to pause this video. You're always encouraged to give things a try and then to come back and see my versions of the solutions. So right now we have 3 left, D, E, and F. So I'm going to go over those in a little bit, but remember, if you will, if you're willing, pause these videos and give them a try. And then, if you get stuck, that's fine. You can always see how to get unstuck by watching the rest of the solution. Or you can see how far you get, and maybe you'll surprise yourself and get the whole thing. Okay. All right, so for those who have now returned or still watching and waiting for the solutions for the next one, for D, if I write out some terms, I'm not going to write n equals 0, n equals 1, n equals 2 again. I'm just going to write them out. So for n equals 0, I get -2 to the 0, which is +1, over 3 to the 0, which is +1. For n equals 1, I get negative 2 to the 1, which is negative 2 over 3 to the 1, which is 3. And I'm just doing it for just a few of the n values. I'm writing them out just so I can see what's going on there. For n equals 2, I get positive 4 over 9. And for n equals 3, I get negative 8 over 27. And if you haven't done so, it's nice to verify that these are in fact the numbers. Okay, so what is going on here? Well, it's definitely alternating. So we got the alternating part down. It's right here, alternating. Do the terms get smaller? Do the terms, the absolute value of the terms, do they get smaller? The tops are 2, 4, 8. So the tops are 2, 4, I guess 1, 2, 4, 8, 16. They're powers of 2. And the bottom are powers of 3. So 3, 3 squared, 3 cubed, 3 to the 4th. So the top is going up at a rate of 2 to the n. So this is 2 to the n larger on top. And it's 3 to the n larger on bottom. Right? Each time the top gets multiplied by 2 and the bottom gets multiplied by 3. You can see 1 times 2, 2 times 2 is 4, 4 times 2 is 8. Each time the top is getting 2 times larger, or 2 to the n larger, right? And then the bottom is going 1, 3, 3 times 3 is 9, 9 times 3 is 27. We're getting 3 times bigger on the bottom. So the top is getting 2 times bigger every single time, and the bottom is getting 3 times bigger every single time. So that means the bottom is getting bigger than the top, right? The bottom is increasing at a faster rate than the top. So the bottom increases let me write out increases so people can read it, increases faster than the top. So what does that mean? That means the bottom is getting larger and larger. So bottom is getting larger. Bottom getting larger. Bottom denominator, if I use the official word, getting larger. That means the fraction is getting smaller. And what does it mean when the fraction is getting smaller? That means we have now verified that the terms get smaller. So we have done the terms get smaller because we know that the bottom increases faster than the top. The bottom getting larger means the fractions are getting smaller. All right, so we've done the first thing, alternating, yes, check mark. The absolute value of the terms get smaller, yes, check mark. Now let's try the limit as n goes to infinity of this series. And let's get rid of the negative sign again. So we have 2 to the n over 3 to the n. So we have to do this. So 2 to the n over 3 to the n, if I stick an infinity, 2 to the infinity is equal to infinity, and 3 to the infinity is equal to infinity. So we have infinity over infinity, which you could use L'Hopital's rule now to simplify. The problem is when you differentiate 2 to the n, you still get 2 to the n. You get 2 to the n ln 2. And if you differentiate 3 to the n, you still get 3 to the n, and you get 3 to the n ln 3. So differentiating doesn't really simplify this. So although we do get infinity over infinity, that is correct. Using L'Hopital's rule to simplify this isn't going to get you very far. Using algebra to simplify this will actually help you quite a bit. So this original limit here, 2 to the n over 3 to the n, if you remember your algebra skills and the way we combine or simplifying exponential functions, 2 to the n over 3 to the n becomes 2/3 to the n, right? 2/3 of the n is the same as 2 to the n over 3 to the n. And why does this help? Because you have a number that's smaller than 1. So you have a number, it's a decimal or fraction being raised to the n. You have a number getting smaller and smaller and smaller. So this goes to, it goes to 0. It goes to a number less than 1. So this is less than 1. I'll just say this. It's a number between 0 and 1 raised to the n, which has to go to 0. Think about any fraction. 1/2 times 1/2 is 1/4 times 1/2 is 1/8 times 1/2 is 9/10 times 9/10 is 0.81 81 hundredths times 9/10 is, it gets smaller, smaller, smaller. Let's see, it's 0.729 over 1,000. Every single time you multiply a fraction by a fraction that's less than one, it's going to get smaller. Every single time you multiply by a fraction which is larger than one, you're going to get larger, right? So multiply by smaller numbers, less than one, you're getting smaller. So we know the limit here goes to 0. So that means that the series converges. So this time I'll write out the original series instead of just writing out org. What was the original series? So we know that this series of -2 to the n over 3 to the n converges by the alternating series test. All right, so because it converges, we get to play the bonus game, which is okay. Of course, my board work here is just horrendous. I don't have room, so I'll just make a line here. So the bonus question is it conditional or is it absolute? So conditional or absolute. That's our bonus question if we have an alternating series that converges. So we take the limit as n goes to infinity of no, we don't have the limit. I keep doing the limit thing, but we're taking the series of this thing. And we're getting rid of the negative signs here. So we get 2 to the n over 3 to the n. The way we write that mathematically is we put like an absolute value bar here saying, let's get rid of all the negative signs and look at the series just as with positive values. So we get 2 to the n over 3 to the n. And now you have to go back and think about, how do I know if this thing converges or diverges? And again, we can use the same simplification technique. We can use our algebra to write this as 2/3 to the n. And that may or may not look familiar to you. This is called a geometric series. It's the a times r to the n type series. In this case, our a value is 1 because there's nothing in front. And our R value is 2/3. It doesn't really matter what the A value is. Even if you didn't recognize the A value, it's not important as to whether this thing converges or diverges. The R value, the part that's being raised to the n, is the only thing that matters if this kind of series converges or not. If you have an R value, if you have the base of the exponent value, which is between 1 and -1, or let's just say less than 1, and greater than -1, right? So if it's a decimal or a fraction that's less than 1, and then we know it converges. This converges by geometric series test. Sorry, I'm running out of room. So we have an original series that's alternating converging. When we got rid of all the negative signs, we get a new series which is still converging, in this case by the geometric series test. So it converges by the alternating series test. We get rid of the alternating part and it still converges. So therefore we call this absolutely convergent. So our original series is I'll write the verb there, is absolutely convergent. Again, I'm really sorry I can't write this in a really neat way. Just trying to explore here, and I don't give myself enough space on these lecture notes, as you probably know if you've watched previous videos. All right, let me zoom out so people can see sort of a screenshot of this solution right here. And this was all example D on this alternating series, and it is absolutely convergent is our answer. All right, I get 2 more examples for you, and again, no room to put them in. So I'll just do F down below a little bit further. So I will just rewrite it, and I'll do E down below. So maybe I'll write F down here. F is our series. It goes from 2 to infinity negative 1 to the n, so classic positive negative thing, negative 1 to the n. And then on the bottom, we get n and then ln n squared. So I'll do f after e, but I'm going to write e right over where f is. So we're not going to lose f, even though I'm going to write over it. So I'll just get rid of this for the moment and move it down there. Okay, so now I'll do e. Let me zoom in a little bit, and you can maybe perhaps see it better on your device. So this is cosine 2 pi n over the cube root of n. That's this particular series. So let me zoom in a little bit more so I can see it too. Okay, so now we need to do the alternating series test, assuming that it's alternating. You can see the cosine in there. We saw a previous problem with a cosine in there, and when we figured it out, it was positive, negative, positive, negative. So we know that this thing, even though it doesn't have a negative 1 to the n, these trig functions, they oscillate back and forth, so they're good candidates for alternating series as well. All right, so as I've recommended many times, let's write out some terms. So we're starting with n equals 1. If you can see the lower limit on the series is n equals 1. So I'll start with n equals 1, and then 2, and then 3, and maybe I shouldn't use red here. I'll use blue. N equals 1, n equals 2, n equals 3, n equals 4, etc. So for n equals 1, I get cosine of 2 pi times 1, which is 2 pi, over the cube root of 1. Cosine 2 pi, again, grab a calculator if you need to, but 2 pi is a full circle. The x value there is positive 1. So this is 1 over the cube root of 1. I'll just leave it as the cube root of 1. I know it's 1, but we're going to get cube roots of 2 and things like that. So it's just nice to see the pattern if you don't simplify it. All right, 2. So if I put 2 in there, I get cosine of 2 pi times 2, which is 4 pi, over the cube root of 2. So I plug in 2. So what is cosine 4 pi? Well, 4 pi is, 2 pi is one revolution. 4 pi is another revolution. So we're back to the beginning place, which is the positive x-axis where x is 1. So cosine of 4 pi is 1. And the bottom is the cube root of 2. It didn't alternate, but that's okay. It doesn't have to alternate like in the very beginning. It just has to alternate at some point, positive, negative, positive, negative, positive, negative. So we just have to say, okay, starting at n equals 2 or starting at n equals 3, starting at some point, it's always going to be positive, negative. So that's all we need. So let's make sure that actually happens. So I plug in 3, 2 times pi times 3 is 6 pi. So I have cosine of 6 pi over the cube root of 3. Again, you can think about the rotations of a circle. 6 pi is 3 complete rotations, each rotation being 2 pi, or you can grab a calculator. Cosine of 6 pi is positive 1 over the cube root of 3. And the next one we'll do for sure is cosine 8 pi. If you do understand trigonometry, if you understand the idea of like circle rotations, you will very quickly understand, oops, that's the cube root of 4, not the third root of 4, the cube root of 4. You will understand that each time I go an additional 2 pi, I end up in the exact same place. So if you use your calculator, it's kind of surprising. Oh, I got 1 again, because you're not really seeing what's going on. But if you just see, okay, well, the cosine, just the x value on the unit circle. If I go around 2 pi, I'm back to the exact same x value. If I go around another 2 pi, I'm back to the exact same x value. So it's very easy to see that this is always going to be the same 1, even though the bottom does get larger. Okay, so this is not alternating series. This is not an alternating series, not alternating series. In fact, this cosine 2 pi n thing doesn't do anything. It's always equal to 1, right? So we have this original series, n equals 1 to infinity. And then we do cosine of 2 pi n over cube root of n. And we know that cosine of 2 pi n is 1. It's always 1 because each time you do a 2 pi revolution, you get back to x equals 1. So this is the same as n equals 1 to infinity of 1 over the cube root of n. Okay, so we don't have an alternating series, So we may not use the alternating series test. This is not a one where we even need to look at whether things are getting smaller or not. It's not alternating, so we can't use that test. So we got to use one of our old tests. Well, you may now start to realize because we have an n here and it's raised to a power, this is a traditional kind of a series called a p-series. So we get n equals 1 to infinity. Cube root of n is 1/3 exponent on n. So that's how we write it in mathematics. So we can see the number there, 1/3 exponent. And this is a p-series. P-series are 1 over n to the p. Right? That's what a p-series looks like. This is a p-series. Our p-value is 1/3. We know for a p-series, if the p-value is less than or equal to 1, right? In this case, it's less than or equal to 1, then we know it diverges. If p is greater than 1, we know it converges. That's the p-series test. If you have this kind of power function, 1 over n to the p, n is the variable, p is the number, and that number, that exponent there is greater than 1, we know that the series converges by the geometric series, by the p-series test. If we know p is less than or equal to 1, we know it diverges by the p-test. All right, so we're done. We know this thing diverges. It wasn't even an alternating series test in the first place because it didn't alternate. Even though I put it here in the alternating series examples, I did intentionally try to put one that looked like it might alternate, but it doesn't. And with further investigation, it actually just diverges because it's a p-series where the p-value is less than or equal to 1. So our original series, n equals 1 to infinity of this cosine 2 pi n over cube root of n thing diverges, and it diverges by the p-test. Okay, that brings us to my final example for these lecture notes. Our example F that I transported down here so I'd have enough space to write the previous one. So this is negative 1 to the n over n ln n squared. A lot of you will recognize the negative 1 to the n part as a dead giveaway that this thing is alternating. I'll still write out a couple terms. We start with 2. So n equals 2 is our first term, according to the lower bound of our series. Negative 1 squared is positive 1. On the bottom, we have 2 ln 2 squared, which I don't know what that is. It's some number. Then we do the next one, ln n equals 3. We get negative 1 on the top because you get an odd number of negative 1s. And on the bottom, you get 3 ln of 3 squared. And then we're going to get, legible. And then for n equals 4, we get a positive 1 over 4 ln 4 squared, etc. So we can see that it does alternate. It wasn't that much of a mystery of whether it alternated or not because it had that negative 1 to the n thing on top, which is kind of a dead giveaway that we're going to be alternating back and forth. Okay, so we know it's alternating. We need the terms to get smaller. We need the terms to get smaller. And of course, we mean like the positive versions of them, not the positive negative versions, the absolute value of all those terms. All right, so do these things get smaller? It takes me longer to write them out than I think it takes some people time to think about how they know the terms do in fact get smaller. So it's an old argument that the bottoms are getting larger. So when the denominators get larger, overall the fraction must get smaller. So here we know that the bottom get larger. I mean, denominators, if you want to be official, the bottoms get larger, so the fractions get smaller. So, do the terms decrease? Yes, they do. Do the terms get smaller? I mean, the question is yes, they do. Right. So we know the terms get smaller. We know it's alternating. And the last thing we need to know is does the limit of that sequence does it go to zero? Right. We need to know that as well. So we're going to get rid of the negative parts and focus in on the absolute value of this sequence. And well, the top goes to 1. It doesn't change because it has no ends in it. The bottom is infinity times ln of infinity squared. And again, if you remember your pre-calculus, you might remember that the ln graph looks like this. And natural log of x tends to infinity as x goes to infinity. It just keeps going up and up and up and up. It doesn't have like a upper limit. So we get infinity times infinity squared, which is infinity. And that's definitely 0. So does the limit go to 0? Yes, it does. So we know it alternates, we know it decreases, the terms get smaller, and we know it has a sequence that goes to 0. So we now know that our series, that the 3 little circles is like conclusion, thus our series -1 to the n over n ln n squared converges. Yay, converges. Okay, and converges by the alternating series test. We're supposed to say the reason why we know it converges. So the reason I know is we did the steps of the alternating series test, and it passed all those components, so we know that it converges. And because it converges by the alternating series test, we have our bonus question. So now, so is it conditional, or absolute? That's our bonus question. That was a question we get to answer if they tell us that if we find out that the alternating series converges, then we can determine whether it's conditional or it's absolute. All right, so how do we do that? Well, we look at the same series, but without the negative part. So we look at the series. This was n equals 2 to infinity. And we're just going to write, and without the -1 to the n part, we're going to get rid of that. We're just going to write 1 over n ln n squared it. So we have to find out, does this converge or diverge? Right? Converging would be absolute convergence. Diverging would be conditional convergence. I should write that diverge or converge in that order so the arrows match up nicely, but I think you are getting the idea. So we need to find out this new series, this one right here, does it converge or does it diverge? It's not really a p-series test because although it has an n to the first power, it also has an ln n. So it's not really a p-series test. It's not really a geometric series because it has to be r to the n, where r is a number. There's no number raised to the n power. We can use something called the integral test. So we use the integral test. The integral test says if you can integrate it, then you can find out whether the series converges or not. So we use the integral test. So integral test basically says if you do the integral of this, formula, if this thing converges, then the original series had to converge as well. If this thing diverges, then the original series, they converge and diverge the same way. So we can do the integral instead of doing the series because we know a lot of integration formulas. We practice a lot of integration, so perhaps we can use integration. It is an improper integral, so we got to do some, little wordsmithing here. We do a limit, and we do 2 to b instead of 2 to infinity. That way we're plugging in numbers instead of plugging in nonsensical objects like infinity. Okay, so we're doing a limit as b goes to infinity, and we have this critter that we need to find the antiderivative of. And the way we're going to do that is by substitution. So we're going to let u equal ln of n. That's n. We take the derivative. The u is the output variable. The n is the input variable. So it's du dn is our derivative. The derivative of natural log of n with respect to n is 1 over n. And then we're just going to solve for dn. So that's our version for dn that we're going to plug in for dn. We have a version of u it's equal to ln n that we're going to plug in for ln n. And then let's do see what kind of washes out in the result. So we have an n here. ln n is u. So ln n squared is u squared. Right? ln n is u. ln n squared, u squared. dn is, well, we know it is, right? dn is n du. So by using substitution, we can try to simplify this thing. And in fact, this simplifies quite dramatically, because we have an n and an n. We have an n on the top and divided by n on the bottom, and those n's will divide to equal 1. So we have this limit of 1 over u squared, which is just u to the negative 2. And we can anti-differentiate u to the negative 2 just by using our normal power rule. So it's u to the negative 1 over negative 1. Let me give just a little bit more space for that limit. So we have the limit. We get u to the negative 1 over negative 1. And this goes from 2 to b. Now, please remember, these values are n values, right? We have n equals 2 to n equals infinity. We never change these values. This is n equals 2 to n equals b. So n equals 2 to n equals b. You may not plug in these values into u because they are not u values. They are n values. So you need to either change them into n values, or you'll need to substitute back in terms of n. I'm going to substitute back in terms of n. So I get the limit as b goes to infinity. U, remember, is just ln n, right? So I can just put in the ln n there. I'm going to write on the bottom because it's u to the negative 1, which means it's on the bottom. So it's 1 over negative ln n from n equals 2 to n equals b. Now we can plug those things in. I plug in b, I get 1 over negative ln of b. I plug in 2, so minus 1 over minus ln of 2. So I plug in my top and bottom limits, subtract, and then I'm going to take a limit. So what happens as b goes to infinity? As b goes to infinity, well, again, ln b is a function that goes up without bound, goes off to infinity. So this becomes 1 over negative infinity, officially. And then this is minus a minus, which is plus 1 over ln of 2. Well, 1 over any version of infinity is 0. So this limit is going to end up being 0 plus 1 over ln 2, which is, of course, just 1 over ln 2. So this is equal to 1 over ln of 2. I'm going to have a little arrow here going to 0, just so I can communicate where that thing went to. So what did we just discover? We just found the integral, not the sum, not the series, but we found the integral of ln 1 over n ln n squared. We found the integral of the same formula as our series. So our series was this. We took an integral of the exact same formula, and we got a number. We got 1 over ln 2. So that means the integral of 1 over n ln n squared converges. But the integral test says if the integral converges, then so does the original series. So both the integral and the summation, they both do the same thing. They both converge. All right. So now we have our final conclusion. We now know on this is example F. We now know that we have an alternating series where the terms get smaller and the limit goes to 0. So we knew that we have a series which converges. We have a converging alternating series. Now we do the additional question of, is it conditional or absolute? To do that, we look at the series without any negative signs in it. So we looked at the series without negative signs. To evaluate this new series without any negative signs, we use the integral test. That new series converged. It converged, right? By the integral test, the new series converged. So therefore, the original series, so I'll write it here. So the original series, -1, I gotta get rid of the circle thing. The original series, -1 to the n over n ln n squared absolutely converges. Absolute converges. Because when we took away the negative signs, it still converged. All right, so I squeezed that in there. Hopefully you can follow what I just said, and I will zoom out a little bit so you can see sort of the steps here for part F. Part F was a series that was alternating and it was determined to be absolutely convergent. This is the end of the video for alternating series test and for conditional and absolute convergence. Hopefully this was helpful. Hopefully if you do have any questions, you will reach out to me either by email or dropping by my Zoom hours so I can help you understand this and you can do really well on these kinds of questions. I hope you have an enjoyable day and perhaps I'll see you in the next video.